So we'll look at some differences. We looked at sodium borohydride and lithium aluminum hydride in the last unit. And in that particular unit, they effectively acted the same. We didn't really see a difference between them. This unit, we can actually differentiate that. So before we start looking at how they differentiate, how are they different from each other? Or how are they similar to each other? What do we have? Say it again, Lorraine. Cool. So primary chemistry for both of these is that they're going to supply H minus. That's our primary focus with them. Since it is negatively charged, we have the potential of it acting as a nucleophile and or a base. What is the primary goal for the hydride in both these reagents? So are they both nucleophilic? Are they both basic? Do they do both? Do they do just one?
They're both nucleophiles.
Yeah, they're both nucleophilic. That is our primary goal. Man, this pen is only half working. Interestingly enough, the lithium aluminum hydride will also act as a base. That is definitely not its intent. Its primary goal is to have it act as a nucleophile, but it will act as a base. Why do you think lithium aluminum hydride would act as a base also? We don't need to get super fancy with in fact, I would argue we don't need to get into any of the real chemistry terms.
The negative hydrogen is so strong that it can act as a base.
The hydride coming from lithium aluminum hydride is so negative that it can now also act as a base. So that's our simplest explanation behind that. The deeper question is going to become, why is it so much more negative? Because it's still the same element. Shouldn't it be just as negative? And that now pushes into the difference between these. So before we get into that difference, what are we typically reacting these with? What was that? True, an electrophile. Which functional group, though? We're looking at a polar pi bond. Okay, our best example to go with in this would be that carbonyl. Okay, so you are right, we're looking at that electrophilic carbon as being our site for both of these. Okay, once we've established that, now what's our difference between sodium borohydride and lithium aluminum hydride? Keep it simple first. Really simple, like you don't have to think about anything. You could just look at what's drawn on the screen to figure out a difference. Okay, so we've got a couple things that we can look at. We can look at the boron versus the aluminum. Okay, that is very clearly a difference between these. The question now becomes, how would that have an effect in the grander scheme? Well, what is the difference between boron and aluminum? Right? We're going to get a difference in electronegativity. And we'll get a difference in size. So if we're going to consider electronegativity, what do we see between boron and aluminum? Boron is more electronegative than the aluminum. How would that affect our hydride?
Easier for the hydrogen to take the electrons.
Okay. If we're looking at that difference in electronegativity, the hydride is going to stay the same in both cases. If we look at boron, since boron is more electronegative than the aluminum, it's actually holding those electrons a little bit tighter. And if it holds the electrons a little bit tighter, what does that do to the H minus?
Is it more, less minus?
Okay, so we could go with either more positive or less minus. Less minus is probably the most appropriate response because we're still looking at it as a negative. Okay? Because boron can hold the electrons in that bond just a little bit tighter than the aluminum. Right? So because of electronegativity, the hydride in our sodium borohydride is less active. Cool. You also know there's a size difference between our boron and our aluminum. How is that going to manifest? Okay, it's a longer bond. So that if we try to draw a little bit more to scale what's going on here, we get a longer bond. How is that going to affect our reactivity? Again, what was the reactivity?
Pretty high. I mean, this is just
It was our H minus, was our reactivity. And if we now make that bond really long, and the aluminum's not holding onto the electrons, that hydride is now more exposed and more likely to react. So by subtly changing that kind of central element, boron to aluminum, we can drastically change the effect of that hydrogen. Those, I would argue, are probably the biggest differentiators that you need to be worried about, because those are the ones directly connected to the hydride. So that's what drives their chemistry all the more. Kind of makes sense? Okay. Is there another difference between the two reagents? Oh yeah, we've got sodium versus lithium. Are the sodium or the lithium connected to the hydrogen?
no.
No. So should they have an effect on the reaction?
Yeah.
Okay. That's interesting. Why do you think they should have an effect on the reaction?
Still floating around.
Okay, so they're still present. If we talk about sodium ions, how often did we evaluate them when we talked about the strength of a base? Yeah, we didn't talk about it at all. Okay. We could talk about them real quickly. Sodium hydroxide versus potassium hydroxide. What do they both supply? I accept the positive, but when you're looking at sodium hydroxide and potassium hydroxide, the primary chemistry is the negative on that hydroxide, right? And in both cases, we're supplying hydroxide. And so in both cases, we would expect them to act as strong nucleophiles or bases. What would the difference in reactivity be between those two compounds?
Sodium would be more reactive.
Okay? And this becomes an interesting dilemma. If we talk through this, we say, well, which one should be the stronger base? Well, they're both supplying hydroxide. Why should it matter? It matters because the counter ion is also doing something. We're talking about sodium versus potassium. What is the difference between sodium and potassium?
Their size.
Their size. And because potassium is so large, what happens to the admittedly weak ionic bond between the potassium and the hydroxide? It becomes relatively longer, therefore making that interaction all the weaker, therefore making the hydroxide all the more active. And so when we talk about base strengths, which of these is the stronger base? Potassium hydroxide. It's a relatively subtle effect in the grand scheme, so we typically don't talk about it that much, or at least I haven't talked about it that much. If we go to our sodium hydroxide, our sodium borohydride and our lithium aluminum hydride, we have a similar situation. Okay, I would argue it's one step further removed. At least in the hydroxide, our metal was directly connected to the reactive element. When we're talking about our sodium and our lithium, they aren't directly connected to the active atom. If anything, they're coordinating to the boron, where our negative charge, formal negative charge, is associated. And it's the hydride that floats off. So how would changing sodium to lithium change the reactivity of these individual systems? If they aren't reacting with the hydride, what could they possibly react with? Say it again. What oxygen? From our polar pi bond, we have that oxygen. Okay? The lone pairs on that oxygen are partially nucleophilic. And they could share with either the lithium or the sodium. Because they now share those electrons with the lithium or the sodium, what does that do to the polar pi bond?
Is the carbonyl more electrophilic?
Yeah, it makes the carbonyl more electrophilic, so we'll just say metal here. And therefore, that solution or that carbonyl becomes more active. So when we're looking at the sodium and the lithium, it's less how they're directly affecting the reagent, it's how they're actually chemically reacting with whatever we're trying to talk about. Right? So in the case of sodium, we're going to have a metal bond, an ionic bond. In the case of lithium, we're going to have that ionic bond. What's the difference between our sodium and our lithium?
More lithium coordinate around oxygen.
So the more is going to become an interesting question because at this point we're really only stating you have one. And as soon as you drop one on there, we generate a positive charge. It's technically a bit hand-wavy, too simplistic, and you're right, you could potentially fit more lithium. But why could you potentially fit more lithium? The characteristic difference between our sodium and our lithium happens to be size. Okay? That size differential, with it being smaller, is less how many you can fit around it, and more, if we color code this out,
Bond more, I guess, stronger, I guess.
in the case of the lithium, it's a shorter bond, which makes that bond stronger, which then makes the pi bond that much weaker. So the lithium reagent, or the lithium counter ion that we would just hand wave away as the counter ion and we don't need to worry about it as a spectator, actually has a role to play in making lithium aluminum hydride that much more reactive. Which is kind of neat. And if you go back to how we're evaluating this, we're going back to the fundamental principles and differences between those individual atoms. Note we're not talking about resonance or induction because we're looking at single atom comparisons, which is why we're starting with electronegativity and size. Kind of makes sense? We just looked at sodium borohydride and lithium aluminum hydride. Why is lithium paired with aluminum hydride? It's a very weird question to ask. Could I have had sodium aluminum hydride and lithium borohydride? Absolutely. Right? And in fact, all I'm going through and doing is subtly tweaking the reactivity of those individual species. Enough that lithium borohydride is going to be more active than sodium borohydride, but less active than lithium aluminum hydride. So just changing that ion can subtly change the overall chemical reactivity. Is subtly changing it going to be important? Well, what are they reacting with? What did both of them react with? Running right through the middle of our whole diagram. A polar pi bond, right? How many different functional groups have polar pi bonds? Aldehydes, ketones, esters, carboxylic acids, acid chlorides, right? Acid anhydrides, amides. There's lots of polar pi bonds. And as we go through and change the identity of an R group around our polar pi bond, does that change the electrophilicity of that center carbon? Yeah. So depending on the reactivity of that central carbon, I may want to choose a different reducing agent. Okay? And I've got one way to modify it, by swapping the lithium and sodium with my individual species, okay, with my hydride source. That can change the specificity of the reagent to target a certain carbonyl. The question that might come out of that is, are you responsible for being able to tune which one is which? No. What I want you to be aware of is that there's a multitude of different reducing agents that sit within the family of sodium borohydride and lithium aluminum hydride. And we can tweak the reactivity of the counter ions to change the reactivity of the hydrides. And with those hydride chemistry changes, we can start to change and tune what they're specifically going to chemically react with. Which brings up yet another question. If I look at sodium borohydride, how many hydride nucleophiles are there? Sodium borohydride, how many hydride nucleophiles do I have?
4.
There's 4 hydrides there, which means if I drop sodium borohydride into solution, it has 4 active hydride nucleophiles. It can target 4 separate carbonyls. Okay, but what if I only want 1?
Just put 1 hydrogen.
So there's an interesting statement. If I only want 1 hydrogen or 1 active hydride nucleophile, could I go through and just say sodium BH? No, why not?
There's a missing.
It's got lots and lots of issues. Okay, number 1, we can say it's got a missing octet. Okay, the boron's a little bit weird, but 6 electrons, we'll call its octet, and we certainly don't have that. Okay, so I need something else here. Okay, it can be a methyl. Okay, it could be a phenyl. It could be a nitrile. It could be a ton of different things. Anything that we put there is going to affect the hydride reactivity. And if it affects the hydride reactivity, does that affect our selectivity? Yes. Okay? So one of the things that's very easy to do is get lost in this class of reducing agents, our borohydrides and our aluminum hydrides, and go, well, you switched it to an R group, and now I don't know what happens anymore. Well, is the R group doing the chemistry? No. Okay? It's the hydrogen connected to the boron that's doing the chemistry. And if we push on that structure that we've drawn already, why was the sodium there? To balance out the overall charge, the charge on the boron that was negative. Is that boron in a spot where it would be negative? No, so what do I need to do? Include 2 more R groups. Now I have a reason for that sodium to be present. Okay, I've got my 4 bonds, or my full octet on that boron now. The reactivity is still that boron hydrogen. That drives all of the chemistry. But if we switch the structure to something like this, now everybody loses their mind and has no idea what the reagent does. Well, what was the chemistry? The chemistry is we had an ionic bond between the sodium and the boron. And if we go through and look at the rest of the chemistry around it, the weakest bond there is between the boron and the hydrogen. All that's going to do is supply a hydrogen nucleophile. So I would go through and say, well, where do I want a hydrogen nucleophile to react? I want it to react with a polar pi bond. That's it. Kind of, sort of. Because changing those R groups changes the selectivity, you get tons of these reagents. Okay? Any permutation of those R groups is going to change how this particular, or what this particular reagent targets and reacts with. Okay? You are not responsible for all of them. But you do end up being responsible for...
2 of them, pretty sure.
Oh, shit, you're right. I only remembered 1.
I think I miswrote another one that I was talking about. Yeah. That's what the retains the oxygen, whatever.
Yeah, here, I got this one right. You get this reagent. Right? You might, oh, well, that's not lithium aluminum hydride. You're right, it's not. But where's the primary chemistry?
Hydrogen.
It's still the hydrogen. It's still going to supply hydrides. Why would that hydrogen be negative? Well, aluminum is large. That's an ionic bond. Hydrogen has the lowest electronegativity within all of those bonds. That's the largest differential. That's going to be H minus. That is now a hydride nucleophile. It's going to seek out and react with a polar pi bond. Okay? What polar pi bond should it seek out? Well, we've changed the R groups, which means we're trying to pick something that's selective. This is one I have to review every time. Andrew seemed to remember it. Did I do that right? You're staring at it?
Yeah, it turns
Okay.
an ester into an aldehyde.
So I think I was wrong then.
Doesn't the aluminum need more than a fourth bond?
It does not need a fourth bond. Okay, so again, what's the primary chemistry? Focus on that primary chemistry. And by fourth bond, there's a couple reasons why you might say that. Well, doesn't it need an octet? Well, careful. Where's aluminum in the periodic table? Its octet is fine at 6. I don't need 8 electrons. Okay, well, you might. Well, doesn't it need 4 bonds to be lithium aluminum hydride similar? To maximize that comparison, yes. Okay, but the overall chemistry there is still the aluminum hydride bond. So focus on the ALH, not the rest of that junk.
So the bond is still the most reactive part, even if the aluminum doesn't have the negative formal charge.
True. Yep. So now we could go through and look at these. Right? And I want to pick a reagent that reacts with these. Right? Well, if I picked lithium aluminum hydride, come on, pen. Struggle bus. Lithium aluminum hydride, based off of the last unit, we know targets the ketone and the aldehyde. Okay? So why would I make these weird modifications to it? Instead of being lithium aluminum hydride, I've added these weird carbon groups and got rid of the lithium. Why would I do that? To limit the reactivity. I want it to target something specifically.
So it can only react one time.
So it's only going to react with one of these things. So now the question would be, how do we figure out what those one things are? Personally, my recommendation is that you should memorize this because it's going to show up. Okay? You have something that's very specific to a targeted functional group. So you should memorize this. Okay? How could we go through and kind of reason our way through it? Well, how many hydrides do I have here? I have 1, which means if I reacted these out, don't worry about, I'll call it the blue hydrogen, but it's going to react once. Put our red hydrogen there. What happens in the case of the last one?
The ester, the ether is the leaving group.
Ah, I get this piece kicked off as a leaving group, and what would I end with?
An aldehyde.
An aldehyde. If this reagent reacted with aldehydes, what's it going to do in the second step? Or in this last one? It's going to continue to react. Does that sound particularly selective? No, we're saying it continues that chemical reaction. So if I'm making this weird modification, it probably makes sense to not select our aldehyde, and it actually might make sense to pick this one. because that one's now doing something goofy. Why not just pick lithium aluminum hydride? Because that would have reacted just fine with the ketone. Instead, I'm doing something goofy. Why do something goofy? Because it's producing something that would potentially continue to chemically react. So what we're trying to do is reason through that class and come up with explanations for why we would pick one reagent over another. And in this particular case, what we're saying is, why did I not do just lithium aluminum hydride from the get-go? Kind of, sort of?
Because you want to stop at the aldehyde?
Because I want to stop it at the aldehyde. Right? And my argument that I'm making is that I just want it to stop. I only want it to do one reaction. The only case where I'm getting one reaction that wouldn't have worked with a less fancy reagent would have been this last one. So that last one is the only one that makes logical sense based off of understanding of why we would modify our lithium aluminum hydride or our sodium borohydride. Kind of makes sense?
That's the only one it reacts with?
Yes. Right? Which then sets us up with, well, if I don't want to be able to deal with all this reasoning stuff out, because I'm tired of reasoning through stuff, right? What should I go through and do? Well, one, you could memorize that structure, right? Because you could see the structure pop up. The other thing that you could go through and do is memorize the shorthand name for it, because more than likely, no one's going to draw that structure. It's got those isobutyl groups, which are big, fishy looking tails. They're going to be annoying on a test, so we're just going to say we're not going to draw it like that. We'll write out the name of the compound, or we'll write out its abbreviation. Di-isobutyl aluminum, I'm going to leave it like this for a second, hydride. The name sets you up with its chemistry right away as well. It's the hydride nucleophile. Okay? Diba is what it's being written as within our textbook. It is more colloquially, commonly referred to as dibol, because aluminum has an L in it. So you'll hear reference to dibol, and that's what it's doing. It is a very selective reagent for a single functional group, and it does a single reductive step instead of doing a cascading effect. Kind of makes sense? And as Andrew brought up, there is another one that I honestly don't remember off the top of my head that I believe targets acyl chlorides.
I think.
So we're just going to do it this way. You got good handwriting, right?
I guess, yeah.
Oh, make sure you're not in the picture. Oh, we just moved it.
I'm sorry, what do you want?
You also get this reagent that targets the acyl chlorides. So when I was writing it up, I wrote acyl chloride initially because I couldn't remember which reagent. This one specifically targets the acyl chloride. Note what's happened is they've changed those R groups. Right? Why did they change them? They needed something to target the specificity of a particular electrophile. This reagent happens to specifically target acyl chlorides, and it ends at the aldehyde. And it stops. It will not continue to react with that aldehyde. Okay? Again, how many of these are there? Modify any one of those R groups or the lithium, and you can change the specificity to target a different functional group. Right? So as many functional groups as you can list, there's a reagent that will target it. What I want you to be familiar with is recognizing where the core chemistry is. The core chemistry is that aluminum hydride or the borohydride. And if you're making modifications, it's targeting some specific functional group, some polar pi bond. That's all I need you to pick up out of that. Recognize the core chemistry. Do not get lost in the nastiness that is those T-butyl groups. They're technically more than T-butyl, oxy-T-butyl groups, or the isobutyl that we had up in the previous case. Understand that they're making that modification to target something in particular. Kind of, sort of. And that does sound very nebulous, but again, if you focus to the chemistry that we're trying to address and not the larger structure, this doesn't get lost. You should now be able to look at that chemical, come on, eraser, that chemical reaction and predict an answer. Because guaranteed they will have that aldehyde structure. Ignore it, well, fine. Guaranteed they'll have the alcohol. I would bet they also have this one. Right? And I'm not creative enough to come up with another one off the top of my head. Right? So what you're trying to think through is, well, what's the reactivity of that reagent? Yes, there's tons of nastiness up there, but the reactivity is right there. And if I'm on a super get important, it's H minus. That H minus needs to react with an electrophile. There's my electrophile, so it's going to react with that. I have a leaving group. That's going to leave. That would take me to an aldehyde, but dang, I got H minus. But if it reacted again, why would I use that goofy-ass reagent? Why not just use lithium aluminum hydride? Oh, it must mean that that reagent can't continue to react. Where's this last one coming from? Someone's seeing that piece out there and saying, oh, I'm going to put that on instead. Right? That wasn't part of the core functionality of that chemistry. Kind of makes sense? Okay. Should have asked if we had questions about that before I deleted everything. Hopefully there weren't questions about it. This was supposed to be part of the conversation that we had maybe last week, and then we either ran out of time or I got distracted and didn't remember it. What are we looking at here within a structure?
A carboxylic acid.
Cool. We have a carboxylic acid and an amine. But they're both in the same structure, so what do we have? We have an amino acid. So when we're looking at the acid-base section of this, one of the common things that we'll look at is how this applies to future chemistries. So this could deal with biochemistry. It could also be directly relevant if you're going to try and do any kind of polymer chemistry, because polymers often reference or replicate this chemistry. Right? We'll make this slightly more complicated. So when we're talking about amino acids, what we're looking at is biochem. And in biochem, we've got tons of amino acids. Tons, by tons, I really mean we've got 20 amino acids. Each of those 20 amino acids has an amine functionality and an acid functionality. They also have something kind of in the middle that's the R group. That R group can have an effect in this kind of conversation, or it can be neutral and not have an effect. All of those different positions have some effect when we talk about biochemistry. Okay? Because when we link together multiple amino acids, you will note that we're going to start to lose some amines and acids because we have to link them together. Okay, what do I mean by that? We could go through and do a nucleophile addition elimination where my nitrogen acts as a nucleophile and the carbon of my carbonyl acts as an electrophile. So a second molecule comes in. Should I draw? Ooh, I have to draw it that way. That nitrogen comes in, we'll call that H2, does a nucleophile attack, or the nucleophile addition, followed by an elimination. And what do we get if we cleaned all of that up? A couple different names we could use for this. That did not do what I wanted it to do. Fine. Because we've now put two amino acids next to each other and linked them, we now have a dimer. Right? We could also reference this as a protein, because proteins are combined of amino acids. Right? Most proteins are much more extensive, but if we take just the individual amino acids, there's some information that gets lost through this process. If I looked at my starting material, I had 2 amines and 2 acids. If I look at my product now, I have 1 amine, 1 acid. So I've changed some of the dynamics of the reactivity of the system by linking those together. Do those dynamics matter? Well, where are we expecting to find these things? Where would I expect to find amino acids or proteins? In the body. Okay? So if we go to the body, why would that matter? Well, what's the majority of the body made out of? Water. And the majority of what we're talking about in this class is organic chemistry. And what happens when we take organic materials and we mix them with water? They're insoluble. They don't mix. Right? But if this is organic chemistry, something's got to change because we know this happens in the body. Okay? Not all organic materials stayed in an organic layer. We could get them to move around. How could we get them to move around? We could run some acid-base reactions. So if I wanted benzoic acid to become water-soluble, I add a base. The base removes the hydrogen. That makes it ionic. Just because I got a slightly funny look from that. We'll draw that out. I could add my base. The base removes the hydrogen, the acidic hydrogen, which is now ionic. That ionic compound is now a salt, and what do salts do? They dissolve in water. So we can change the solubility of our organic compounds by changing acids or bases. Okay, I add an acid or I add a base. Is our biological system going to do that very much? Probably not. Okay? Because if we add acid to our biological system, what does it typically do? Neutralize is a nice way of saying it. If you just poured acid all over yourself, what's going to happen? It's going to dissolve. Okay, so when we're talking about the organic chemistry, just add an acid or a base and we'll change it, that becomes very, very problematic. Okay, because if we add too much acid or too much base, it can't get buffered and we destroy things. Why are we destroying things? Where's our body happy? What's the middle? What's the middle of acids and bases? It's a pH of 7. Okay? Which is going to change all sorts of dynamics between this. Because if I'm at a pH of 7 now, that is going to have an effect. Just like if we added acid, we were at a pH of we'll go with 2. Or if we were a base, we'd be at a pH of 9. That works. Okay? Those pH swings change the protonation state of our individual molecules. That protonation state is dependent on its chemical reactivity. So what we would do is we'd go back to our protein and we'd say, well, what is it actually looking like at pH 7? We drew out the molecule as shown up here because everything's neutral. We wanted everything to be neutral. Why? Because that's the world we live in organic chemistry. We make stuff neutral. Biology does not make stuff neutral because if it's neutral, it doesn't dissolve And we have multiple problems of layers and mixing and all sorts of issues. Okay? So if we're at a pH 7, how does that change this structure? Okay? The carboxylic acid, okay, this becomes a fun one. So we've got our acid. Picked acid as red. A little bit of color coding in here. Our acid is acidic, right? It has that acidic hydrogen. Okay? And if we're at a pH of 7, I just heard that what happens is it's no longer protonated. Why? Why do I know to remove that hydrogen?
Because if it was an acidic environment, it would have.
And this becomes a weird, you know the answer, so that's great, but the why becomes problematic.
If the hydrogen was there, it would be a higher pH.
Would be a what pH?
A lower pH.
Okay? If the hydrogen was still on the structure, we have to be in an acidic environment. So really what you're trying to do is you're making the comparison between the name acid and you're making a comparison to the solution. And if my solution is a pH of 7, is that higher or lower than what I've decided acid is? Higher. So I'm in a more basic environment than my acid functional group is, which means what should I do to the hydrogen? I need to remove it. I need to run that acid-base reaction. But what if my solution is now acid? There's no reason to remove that hydrogen. And so what we're looking at for the individual carboxylic acid functional group is its protonation state. Should it be protonated or should it not be? And that is heavily dependent on the pH of our solution and some understanding of what the acid is. Okay? So let's switch to the other side. How about the amine?
It should be normal protein. If it's on neutral or acid, if it's acid. What?
That's a good question. What is the amine? Is it an acid? It has hydrogens.
It's a base. It has a pKa of 9.
Why is it, if it has a pKa of 9, okay, that's a good question. Let's jump on that. pKa of 9. Okay, I love that you're bringing in pKa's. We're quantifying this, and this is where this one gets nasty. What is the pKa of water? I'll accept 14. Sorry, 40 is way too high. Okay, I would usually say 16. I think it's officially 15.7. It does depend a little bit on what scale you're looking at. So if you have a pKa of 9 for the amine, is that more or less acidic than water?
It's more.
It's more acidic than water.
Yeah.
But you just said the amine should act as.
A base.
Isn't that a conflict?
No.
Okay. So you brought up pKa's for the amine. You didn't touch pKa's for the acid.
Well, it would be a 4 on a carboxylic acid.
Ah, okay. We didn't talk about the pKa for the acid because what did we understand about the carboxylic acid functional group? It's acidic. We didn't need to evaluate pKa's because we knew it was acidic. Right? And we knew it was acidic because it says acid. Does the amine tell us it's acidic or basic?
No.
No. Therein lies our issue with the amine. So we have to understand something about its reactivity to be able to predict what's going on within it. So before we even get into the amine, how about let's double back to the acid and make sure that because we have a thing that we trust, we know, can we bring pKa's in such a way that we now understand how to apply pKa's so that when I move to the amine, I can apply that logic system and know it works. Does that make sense? Okay, so for the acid, we said it dealt with protonation states, right? So for the acid, Shoot, we'll make that black. Okay, is this protonated or deprotonated? It's protonated. Okay, so this would be my protonated state. What happens if it becomes deprotonated?
That's the conjugate.
That would be the conjugate base. Awesome. Okay, when does that happen? Doesn't have to be basic.
Always.
Just not acidic. So
Ooh, not acidic. Not true. Because I can have acidic conditions where it shifts too.
More often.
Okay? So we had a reference here. This was the conjugate base, so we could reference this as the conjugate acid, right? Okay? And we said not acidic or basic. We're trying to deal with those. And ultimately what you were referencing in that case is what's going on within the solution. How do we measure the acidity of the solution? I heard someone say it. The paper was not what I heard first. Okay? Our solution is pH. And because Andrew was so kind, how did we understand that this species was an acid? Yes, it was in the name, but we could also reference not the pH, because the pH is of the solution. It's entirely independent of the molecule. pKa. Come on, pen. Okay. Is there some way to relate the pH, the pKa, the conjugate acid, and the conjugate base?
Yeah. With math. And I always figured I'm not doing that.
With math? Yes. Yes. And if you're trying to figure out when and where this happened and how we talked about it, we didn't officially, well, I think it's in the video, but I try to avoid talking about it. You talked about it in 152. It was the Henderson-Hasselbalch equation. I know some of those words. That's good. Okay. And for the record, I'm not very good at remembering it. So it's the pH, because we're typically trying to determine the pH of the solution. So that's usually what we're using it for, at least in 152, is related to the pKa of whatever our substance is. Okay. And minus plus, you just look it up for me? Okay, the log
of the conjugate base, or like A minus, over the weak acid.
and those are concentrations. So when you told me at pH 7 that you knew that structure should be negatively charged, what you actually did was this. You did all of this mathematics to tell me that. You're like, I don't believe you at all. Well, walk through it. Okay. What's the pH? Did we define it?
7.
We said the pH was 7. What's the pKa?
4.
Okay. And the pKa, you're like, I didn't have that memorized. I didn't know what that was. But what you did know is that it was acidic. And because we picked a pH of 7, we knew the pKa had to be
Below 7.
below 7. Okay. How would we figure it out? We'd look up the pKa for that actual structure. Okay. And this is something that theoretically you'd be asked to do in biochemistry. If you go back through all the acid-base lectures that I've talked about, I've said I highly encourage you to memorize the pKa's of our particular functional groups because it can come in handy. Ta-da! Okay. And what is the pKa of our carboxylic acid? 4. Good job. Okay. And then plus the log of all this stuff, our conjugate base over our conjugate acid. We do some math. 3 equals log conjugate base over conjugate acid, right? I don't think I did anything crazy yet. Okay, then what do we do? The ratio of our conjugate base over our conjugate acid is other way around.
10 to the third.
10 to the third power. Okay, 10 to the third power is
10,000.
just 1,000. You got me questioning my life. Okay. Oh, so that's just 3. That's 1,000.
Oh.
Yeah,
10
I
times
got
10
it.
times 10. That's
Yeah. So what does this mean? What does this mean? How could I possibly get a 1,000 number with the ratio of conjugate base to conjugate acid? I have a lot of whatever's in the numerator. What was the conjugate base? Which means, back to my structure, it was negatively charged. That's how we apply it. So what do we do now that we know that that works, right? Okay, because that was our initial gut. We've got the mathematics to support all this. This all works. We should now go through and do what? Let's take a look at the amine. So for the amine, what pH do you want to do?
9.
Pick 7. Let's keep it constant.
Not 9.
Okay, not 9. Okay, we'll pick 7. Okay, now pKa. So we would have to look up the pKa of the amine. Okay, interestingly enough, guess what? Andrew was spot on.
9.
It's about 9. Okay, so now what? Plus the log of my conjugate base over my conjugate acid. Do the mathematics. My conjugate base over my conjugate acid equals 10 to the negative 2, which should be 0.01. What does that mean?
Or acid. Or conjugate.
I have a number that's less than 1. That is only true if I have a larger concentration of the conjugate acid. Sweet. For the acid, we had to go through and say, based off our structures, we knew what was conjugate acid and conjugate base, which means what do we need to do for the amine? The same thing. And this is where things get dodgy with the amine functional group. Okay? Why would they get dodgy with the amine functional group? Let's take a look at it. In our upper left, what do you see on the amine functional group? I see hydrogens compared to 1. Does that matter? As long as you've got 1, you have the potential for it to act as an acid. Done. I do not care how many there are. It is 100% irrelevant. Don't use the number of them to count anything because it doesn't matter. What else do you see on that nitrogen? A lone pair. So if I have a hydrogen connected to an electronegative element, I potentially have an acid. And if I have a lone pair, I potentially have a base. Okay? Nucleophile is technically true, but we're looking at acid-base chemistry right now. So, what is it? How do I decide where this falls?
The stability of the conjugate?
You could try and deal with stabilities of conjugate bases, and we could try and pull something out with that. So here's our NH2. So we could go through and look at it going this way, and it would become our protonated state. Or we could have gone this direction, in which case it would have become deprotonated here with a negative charge. So this sets up an interesting problem because this is the conjugate base of this is my conjugate acid.
Is it like water?
Yes? Yes, water's going to become important. What else is true?
The one on the left is the conjugate acid, in the middle we're the base.
Everybody see we got a dilemma here? Is the amine the conjugate acid or the conjugate base? Okay? It depends. It depends on what? It depends on the local environment it's in which case for OChem, we really didn't care because the local environment could support either one of those depending on what we were evaluating. Only once we add the added restriction of pH. What was pH?
7?
What is pH? This is a hard question to answer. The concentration of hydrogen ions, yes?
In solution?
Better? It's not in solution, technically. It's in a very particular solution. in water. That is the only case where pH is relevant. This is why when you tried to test the pH of the organic layer, I told you to stop doing it, because you can't test the pH of an organic layer because it needs to be water soluble. So all of our pH strips are useless in that respect. What we would have to do is look at the solutions that have passed through to get some understanding of whether it was under acidic or basic conditions. So what this ties back to is what's happening with water. And if we look at water, its pKa sits at 16. Since water is the solvent, water controls the entire environment that we're in. And that control means that in a water environment, that is the only side that matters. Okay? The other side is irrelevant. Why? What happens if I try to mix those two species with each other?
The oxygen is just going to be deprotonated because it would hold the negative charge instead.
If we look at water as our solvent, what's going to immediately happen if I try to mix those two is I'm going to immediately get hydroxide and my neutral nitrogen, because the hydroxide, the oxygen, can stabilize that negative charge better than the nitrogen. Which means adding that strongly basic nitrogen doesn't exist in a water environment. We should never be able to make that en masse within the body. It's just not going to happen. Right? Which means that side of my pKa branch, or my acid-base side, becomes irrelevant, and the only one I care about is what's happening out here. And the pKa for that step is 9. The pKa for the other step is 36. And I'm trusting you on that. It's 30-something, I think. Okay? So that 36 is outside the range of dealing with water, so that chemical reaction doesn't happen. Why does this become important? Well, we said, according to this ratio, the conjugate acid is the one that needs to be present in solution. Which of these two species is my conjugate acid? The one with the hydrogen on it. Which means if I'm at a pH 7, what happens to my structure? It becomes protonated. And because it is protonated, what happens to the charge on that nitrogen? It becomes positive. So that if I now look at this protein in a water environment, what would I expect of its solubility? Well, it's doubly ionic. And since it's doubly ionic, it's doubly a salt, which means longer prison sentence. It is doubly soluble in water. And therefore, this dissolves. This doesn't encounter any issues with proteins coming out of solution. But if I add acid to my skin, what happens? That acid protonates the carboxylic acid side of this, changes the ionic nature, and now what happens to the compound? It precipitates out of the water environment. So instead of having everything nice and soluble in my bloodstream, all of a sudden I have a bunch of solid chunks floating through it. And if you haven't heard yet, solid chunks in your bloodstream is a really bad thing. Okay? Generally, that means death. Right? Okay? So this is why our biological systems tries to neutralize the pH so that we maintain the solubility of our individual proteins through this. So when we now made this dimer, this protein, we only had to deal with one amine and one acid. I didn't have to deal with them both. But in making this protein, what else did I add to the structure? Depends on how you're pronouncing it, but I'm going to trust you were pronouncing that right.
Is it phenol?
It's an annoying thing to go through and say. I would call it phenol.
Phenol.
And yes, I'm trying to be real emphatic on the "ol" part of that, and not phenyl with the YL, because the phenyl could refer to just that piece.
Phenol.
Okay? So I'm referring to it as a phenol, and why should I care about the phenol?
Because it has a pKa of 10-ish.
The phenol has a pKa of 10, which means if I'm going to look at this amino acid at a pH of 7, not only did I have to address the amine and the acid, I also have to address the side chain on my protein. And with the phenol of a pKa of 10, what should happen to its protonation state? Well, how do we do it? Okay, 10, right? So this becomes -3. Add another 0. It's an even smaller state, which means... Did I do that? I think I put all those pieces in there. Which means?
There's more of the conjugate acids.
More of the conjugate acid. So now what's the protonation state for the phenol?
Or
This is the protonation state for the phenol. Okay? With a pKa of 10, what we're talking about is that hydrogen being acidic. So really only the basic functional groups do you have to be really concerned about. The acidic functional groups already start in those kind of states. Kind of, sort of? Okay. So in OChem, what we try to do is bring in the 152 stuff so you recognize where this is all coming from. Okay? That's dealing with what pH of the solution you're at, and you have to understand something about the pKa's of your primary functional groups. The primary functional groups we deal with are the ones that we've talked about, okay, for the entire semester. Those are the ones you should be considering when evaluating this. Do you really want to double back to Henderson-Hasselbalch every single time? No. So, is there another way to go through and do it? Yeah, it's just Henderson-Hasselbalch kind of light. If your pH is lower than the pKa, if I have a low pH, what does that mean? I'm in an acidic environment. So if my pH is lower than the pKa, what should my state be?
The acidic.
It should be the protonated state. If my pH is higher than my pKa, what does that mean?
Protonated state.
Deprotonated state, which is, there was a D in there, right?
Protonated.
Deprotonated? I'm just making sure. Okay. So what you need to be careful of are what are your protonated and deprotonated states for your functional groups. Okay. The vast majority of our functional groups that we deal with start in their acid form. So you don't have to stress about those. Phenol, carboxylic acids, alcohols. All of those start in their protonated state. The one that does not is the nitrogen. The nitrogen, since it acts as a base primarily, starts in its deprotonated state. Kind of, sort of? Okay, and then because we always rag on the chemical engineers for having to deal with a whole bunch of extra crap in their future classes, let's rag on everybody else. When you move into biochemistry, you're not looking at the structures anymore because you're responsible for knowing what your 20 amino acids are. Right? And we don't want to have to draw out, if we have a side chain or a structure of 10 amino acids, we don't want to have to draw out each of those amino acids. So what we have you go through and do is we could have you go through and memorize 3-letter codes or the name of the compound. Okay? And you're like, well, that doesn't look like standard nomenclature. It's because it's not. Biochemistry does not have standard nomenclature. It's whatever they felt like calling it the individual time, and they went, ta-da, name. That's how it works. Okay? But to make things better, they're like, there's too many letters in that, so we want to shorten it. So we'll do a 3-letter code. Why didn't you do a 1-letter code? Oh, we did that too. Did I do that one right?
I just did 3.
Oh, okay.
Yeah.
Okay? So you're now responsible for knowing that S means serine, and serine means... I don't know. Biochemist. Serine, is that? God, biologists are supposed to help me out with this.
I don't have to remember this till next semester.
Yeah, I know. Most of you haven't taken biochem. Technically, this class is a prerequisite. So, okay. So you would be oh, did you get it? Yeah, love that. Okay. So you would be responsible for knowing that S meant this. So what they could say is, what is the charge for S at pH 7? What is the charge for S at pH 3? Because we can pick any pH we want. We're changing that. Why would we change it? That changes the protonation state. Why would we change the protonation state? That changes its solubility. Okay? That changes its charge, which means if I wanted to, say, isolate a really important protein away from all the other junk, I could change the pH, and that would allow me to separate that protein from everything else, because its charge state would change. And we could use things like column chromatography to figure those things out. Okay? But where I like this is that that was just a single amino acid. Because you could be asked for a larger protein. You could be asked for the protein that combines serine and histidine and isoleucine and tyrosine. Nope. Tryptophan. Whatever, close enough. Tryptophan and tyrosine. And you would then be asked, what is the charge of said protein? And I would say your answer lies in the one-letter codes, if you were so inclined to figure that out. If you're not so inclined, don't stress about it. Okay, yet worry about that when you get to a biochem class. Just stupid Mike humor. Okay, questions? Okay. Do you have other questions? It's your opportunity, or you keep getting me making up questions. I got a small list. Okay. Small list that, for the record, is, what button am I trying to push? Is coming from questions that I saw within the Smart Work. So if we were to look at which I think is a bit of a misleading question, unfortunately, but we've got a bunch of acid derivatives. We could be asked which of these have better leaving groups. Okay? So the first thing that you've got to do is address where the chemistry is happening. So if we're looking at polar pi bonds, we need to pick a polar pi bond. I would argue the structure at our left, that's my right, it's probably easiest to deal with because our polar pi bond, there's only one. So there it is. Ta-da, there's my polar pi bond. Where's my leaving group? So of course, the carbon.
It's the chlorine,
Why is it the chlorine and not the carbon?
because the chlorine's an electron withdrawing group.
No. I mean, not no, but no.
It's more stable on its own.
Okay, why is it more stable on its own?
It's bigger.
There we go. Okay, so if we're evaluating leaving group ability, what are we being asked to do? First, identify what your leaving group is. So in this case, it's the chlorine, okay? And in that particular structure, I could have had a leaving group of the carbon. Why is the chlorine a better leaving group, Cl minus, better than the carbon? Well, charge. They both have the same charge. What's the next thing? Size. Which one's bigger? Chlorine. What does that mean about its stability?
When we're stable.
It's better able to stabilize that negative charge. That makes it a better leaving group. Does that make sense? So we go to the next one. Again, only one polar pi bond. What's my leaving group? Okay. And this one has a variety of answers. I would argue your leaving group is O. That's it. Okay. That O also happens to be connected to this carbon out here, so that's part of it. So you could call it that ether if you really wanted to. Okay. What's the next? Why is the next one more difficult?
There's two possibilities. There's only gonna be
There's two pi bonds. So just like, oh, we had two hydrogens, so that made it more reactive. No, only one can react. Pick one. And I would argue in this case, there's only one that we should pick. Which of those two polar pi bonds should we pick?
One on the left.
Why the one on the left?
Because I'm reading it left to right, so it's the one.
That is a perfectly valid answer. That's not the answer I wanted.
But
Well,
the
it's
one on the right,
symmetrical
you have to
also,
do the
so-
less arrow, makes it easier
Nope.
to draw. You have to do the electron.
Look at our other structures.
Our
If we
leaving
pick
group
the
is
one on the
right.
left, where's our leaving group?
On the right,
It's on the right. Where's the leaving group in all of our other patterns?
on the right.
On the right. If you picked the other way around, it's not wrong, but you're now making life potentially more difficult because your leaving group is in a different orientation. You're making your brain do more work. And how many of you actually want to make your brain do more work for the exact same reward? Okay? So simplify your life as much as possible. Maintain certain patterns so that you don't have to break out of them. So if we now go through and compare, what's our leaving group on the left? Leftmost structure. Oxygen is what I'm looking for. Technically O minus. What's the leaving group in the middle? Oxygen. What's the leaving group on the right? Chloride. Okay? Is there a difference in charge?
No.
Is there a difference in size?
Yes.
Yes.
Chlorine, larger.
Chlorine is larger, therefore more able to stabilize the negative charge, making the chloride
Number 1 in there, 22.
our best leaving group.
Isn't the charge different actually?
What's that?
Isn't the charge different actually? For the very left. Half.
What you may be asking is something slightly different, and we'll get to that in just a second. So we can double back to your statement. Yes. So if we now try to figure out the other two. So we looked at charge, we looked at size. They're both oxygens, so there's no difference. What's the next thing? Electronegativity. Is there a difference in electronegativity, oxygen and oxygen? No, so there's no difference there. What's the next thing? Resonance. Resonance is now looking at a molecule effect, which means I can no longer just be drawing this as chillin O. I've now got to draw in the rest of my structure so that I can see, is there a resonance effect? That left one does have a resonance effect. The middle one does not. What does that resonance effect do to the effective charge on the oxygen? It reduces it, which means it's more, whoops, come on, pen, more stable than this one. Okay? We don't want to deal with that resonance argument until we've addressed the atom effects first. Okay? Because if you go through, well, that's a -1 and this, or -1/2 and this is now -1, you're going to say that one's more stable. The chloride's still the better leaving. So follow that ranking system down. Does that make sense? So when you're asked this question in smart work, there's tons of possible structures for acid derivatives with lots of different leaving groups. Draw them out, evaluate each of them, charge, size, electronegativity, resonance, induction. All the way through. Slow it down. Okay? Questions? Okay. We'll do a bonus real fast. Not that bad. What's the most reactive thing?
The carbonyl with the adjacent.
Try again.
Negative oxygen.
Oh, the hydrogen.
We have ethoxide. Okay? Ethoxide could act as a strong base or a strong nucleophile. To shortcut this, it's going to act as a strong base. Okay? If it's going to act as a strong base, where's my most acidic hydrogen?
Between the green, actually,
Oh, I love that actually. That was perfect.
it could be that one, and then the other one there, that one.
You have 3 acidic hydrogens. All of those acidic hydrogens are
Acidic.
Alpha hydrogens.
touche. That was a horrible blank space. Alpha hydrogens. Because they're alpha hydrogens, they could all potentially be removed. So how would you decide which one should be removed?
They're more stable.
If it's more acidic. Okay? So when we say try it all, that means remove the hydrogen, evaluate the conjugate base. Make that comparison all the way through. Guess what you're going to discover?
That one.
That one. The blue one's the acidic one. So that's going to put a negative charge there. Okay? So now what could happen?
Wait, why is that one
Resonance stuff.
It has resonance. For those people potentially asking about why the hydrogen out here, I guess I should not point to it that way, the hydrogen out here is not more acidic due to induction, is because it's not induction, it's resonance. There's a competing resonance that comes in that prevents that hydrogen from actually being acidic. So there's our acidic spot. We get that from step 1. If step 2 just puts the hydrogen on, or you draw the exact same structure again, that would be really boring. So what else do you need to find? We don't even need another resonance structure. Maybe. We need to find an electrophile. So where are the electrophiles? Because you said this first.
The resonance structure?
No. You said it first to start the whole question off.
The hydrogen ion.
The carbonyls. Didn't you say that?
Yes, I did.
Okay. Our carbonyls. So which of those carbonyls is going to react?
The one that's adjacent to. Oh, no.
If it reacts
It's not
adjacent, what is it doing?
That's just resonance.
That's just resonance.
It's
So
one that's not adjacent because it will make a ring.
cool. That would exceed the octet. So you break the pi bond. And then because we're lazy,
We'll draw another arrow.
you reform the pi bond and
And push off the ether.
kick out a leaving group. Okay. This should look really familiar. What does this kind of look like?
Oh, that. I don't remember that name, but
Fair. This should look like the aldol chemistry from our last unit. That's because in my mind it is. It is 100% that aldol chemistry. Officially, because it's bringing in an ester into this reaction, it's no longer an aldol because it's not an aldehyde or a ketone. Somebody else went through and said, hey, what if I react it with an ester functional group? Can I now change the name? Yes, apparently they can. And it now becomes known as a Claisen reaction. Then some other jackhole was like, well, but if I do the Claisen reaction intramolecularly, could I call it something else too? Yes, apparently you can. And now you have a Dieckmann condensation. Okay? So tons of different names associated with it. All of the chemistry is effectively the same. Stress about the chemistry, not about the name. With that, we are officially done. So I'm going to, interestingly enough, pause. So what does the PBR3 do? So we have to be a little bit careful with calling it Wittig. When you're saying Wittig, what you're talking about is PPH3, not BR3. So PBR3 converts the alcohol into bromine. Yes. What's the next thing do?
It turns the bromine into MgBr, so it makes it a really good reagent.
Which,
It makes it just a nucleophilic carbon.
whoa, that was a bit excessive. I would argue should just take you to this.
that attacks.
Okay. And then I would double check here. So we've got 1, 2, 3, 4, 5. It's a good thing we double checked. So that should just be a 5-membered ring with the carbonyl. Okay. And with that drawn out, I do actually also want to double check, make sure I didn't lose a carbon when I drew over everything. 1, 2, 3, 4, 5. Yeah, no, it's 5. Make sense? What do you mean what happens next?
Or in their second part?
So the H3O plus is always a follow-on to Grignard reactions. Why?
To kill the rest of the gradient?
To kill any leftover Grignard. So, oh, the next one? Yeah. And interestingly, I don't think your answer was really all that far off to a certain extent. It's going to come down to what does that reagent do? That's the part that's probably confusing you. What's that?
Is that solid?
That is solid sodium. So that's arguably they did the wrong symbol there. I think they did the wrong symbol. It's supposed to be a 0, not a O. It's 0 because what they're saying is that is raw sodium. It's elemental sodium. So what we're talking about is sodium with a single electron on it. What does sodium want to do?
Get rid of it.
It wants to transition to sodium ion. Okay, so officially sodium metal is going to navigate through a radical mechanism. Okay, and we'll draw it out here so that you're aware of it. Okay, where's the most likely place that it could get electrons within that structure?
Hydrogen on the OH group.
It's going to turn out to be that hydrogen. So you get the radical reaction there, radical there. This sets you up with sodium hydride. And yada, 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 with a radical on it. Okay, what could that radical partner up with? Another sodium. Why does that become important? That gets you to the active structure that you cared about. Oxygen with the sodium on it. Excuse me. 1, 2, 3, 4, 5. And if we had the sodium with the oxygen on it, what's actually active there?
Na plus O minus.
You're actually looking at O minus. What could that O minus do?
Attack.
Wow. Break open the pi bond, reform the pi bond, kick out the leaving group. 1, 2, 3, 4, 5. So I just have a 5-membered ring again.
The oxygen is the sixth member.
This ends up being a 6-membered ring because that oxygen is actually part of that ring. The oxygen is connecting carbon 1 to carbon 5.
What are you asking?
I wasn't asking, I was just drawing it just to elicit someone to yell at me. I know you were asleep, so I was waiting for somebody else to yell at me. Okay, that drops in that structure. For the record, that's not a judgment. Just, it definitely sounded like it, but that was not at all the intent. 3, 2, 1. So we end up getting, this is our new bond. And we'd have that carbonyl. And then the dilute H3O plus is again, neutralize your reagents. There ends up being multiple ways we can make this molecule. We just showed one, but you could have, once we had the sodium reacted to form sodium hydride, that's now a strong base. That could just as easily attack another one up there to make your active nucleophile.
Something I was wondering about with this one, when the negative oxygen goes in and attacks the carbonyl, then you have your negative oxygen, your new negative oxygen with the pi bond push up, and 2 oxygens single bonded. And so, why isn't the leaving group the oxygen that just came in? Is it not equal to the other oxygen? Could it also be pushed out? Or is it just because that's really unstable?
So yeah, when we talk about this coming down, we have 2 potential leaving groups. We either got this one, or we have this one. Deciding which one happens is probably going to push to a couple different things. So when you're saying, am I okay with blue versus purple? I don't like it. I'm going to draw it better. Now hopefully blue versus purple makes sense. That both blue and purple are equivalent in their leaving group abilities. Okay? They're both going to generate an O minus. So energetically, which one is favored? There's no energetic difference, okay, as far as delta H's go, right? Because you're not making, you don't have, it's negative oxygen. There really isn't a difference in energy between those two. So why would you favor one versus the other? Okay, well, if we kick out the blue, how many products do we have?
2.
2. How many starting material? If we pick out the purple, how many products do we have?
1.
1. There's an entropy difference here.
So we prefer to have more products, more like the types of products.
You tell me. This goes back to 152 and entropy. What happens with entropy? Entropy always increases. So we're looking at a slight entropy favoring in this particular scenario. Okay. Is this going to be a mess? Probably. Yeah. Because I would argue, well, actually I wouldn't argue that. I was going to start to say you have other acidic hydrogens, you don't really. But yeah, with the radical mechanism involved in this, with sodium trying to stabilize, this is the most likely outcome. But I would like to say I'd be surprised if you cleared a 90% yield. Like there's just a lot of stuff going on. Other possible chemistries that could get in the way. You could have multiple of those molecules attack each other, forming a polymer, instead of doing it intramolecularly. There is a favoring to do it intramolecularly because the 6-membered ring is slightly more stable, or is one of our more stable ring structures. So you could look at that as potentially a contributor to that making that product. Kind of makes sense? Other questions about that one?